Okay, so good morning. This is sort of like, there are two talks back to back. Anna Slobodova, who's from Centaur, is going to tell you about the x86 hardware, and I'm going to tell you about an x86 specification. So as Peter pointed out, these levels in between are points of high leverage, and so we're trying to capture the x86 spec in a complete enough way that eventually we hope to be able to boot an operating system on it. I know that's kind of ridiculous. I don't know that we'll ever get there. Because there are a lot of pieces that you need beyond just the processor ISA. You need I/O devices and so on. So it's a very hard thing to do, at least for sort of formal method-oriented people. Anyway, this work is primarily Shilpi. She's a graduate student of mine. She's about to finish her PhD. I've been participating, of course, in Matt Kaufman. He and I sort of started this x86 specification work about 4 years ago. But probably 3 years ago, she ripped it out of our hands, which was good. Anyway, so what are we trying to do? We're trying to increase reliability. So this is from processor up, okay? So we're talking about sort of low-level software and the specification of this artifact. And then you'll hear from ISA level down in the next talk. So we're trying to build a machine code verification for x86. We're doing it with ACL2, and we're trying to vet our tools on commercial-sized problems. So we're just going to tell you a little bit about it today. And as I mentioned, we'd like, although it may be a dream that'll never happen, to boot some kernel. Probably it makes more sense to boot some simple, something like SEL4 to start there. So maybe somebody will want to help us do that. That probably makes a hell of a lot more sense. We have a lot of collaboration with industry. AMD, Centaur, you'll hear next from Anna, Oracle, IBM, Intel, National Instruments, National Security Agency, Raytheon, and Rockwell Collins. So what we do is we develop core technology. We apply this stuff in different domains, and then these commercial users help us, harden it and make it work on commercial-sized problems. Or we fix it after they tell us what problems they've hit, which, they're not shy in telling us. But there are some substantial number of developers at Oracle and Centaur, So we're trying to increase software reliability just by, being able to do analysis of it. So our plan of action here, we're going to build an executable x86 model using ACL2. We're going to build a code analysis framework based on that. In other words, using the same system to create all the necessary tools and procedures to do mechanized verification, and then try it, so to speak. Okay. So, what's potentially contribution? Well, this framework for doing x86 machine code analysis, you'll see some examples, but just to give you an idea, we just take programs, however they get generated, right out of GCC, LLVM stack, or other pieces of x86. Some of them people have an interest in us analyzing pieces of x86 binary for which they don't have the source, and they'd like to know, certain properties about it. One of the things to make that reasoning possible is to be able to build effective lemma libraries. In other words, if you've got a big bunch of binary, how do you recover what's going on in the binary? That in itself, especially in the cases where you don't have any source, you just have binary, that itself is sort of a challenging reverse engineering problem. And being able to do symbolic simulation and a number of other kinds of things that we do, makes that a lot easier. And of course, we're building what we believe is sort of like a systems effort, which is different than most formal methods efforts. There's a lot of effort we're putting into it initially to try to create something that will be an artifact that will be useful for years to come. We've also been looking at proving and have about how much resources a program needs. So, for instance, one of the program examples I'm going to show you that we did a proof of, we also proved how much memory it takes. So we almost always do that when we do the verification of a program. We wind up doing these other properties, so we know how much memory we've consumed or how much stack is required and so on. You can also use these tools to do information flow analysis. For instance, if you have some piece of data that comes in on some port or something and you'd like to know where it goes, well, we can keep track of it and tell you what it's, sort of colored, if you will. And we would like to, but haven't done anything about. Our model, which you'll see a little bit of here in the slides to come, includes the supervisor paging tables and segment structures, and so all of those provide isolation and in the x86 style. So how do we get the spec? Well, we've been reading these documents. They're very large. This is 3,400 pages, and this is 3,000 pages. And then, of course, we talk to architects. Fortunately, we've had good access to the people at Centaur. Centaur doesn't actually write their own manuals. They just read Intel's and AMD's, but they try to follow Intel. Okay, then, of course, we run tests. So we set particular things, and we try it. We also do a lot of co-simulation. So I'll come to that in a minute. But the model, this model is quite complicated. I don't know how many of you have looked carefully at x86. Most people think of it as sort of, these 8 64-bit registers. I'm sorry, here 16 64-bit registers, and maybe they know of or have heard of the segment registers. And of course, they've heard of the program counter. And if they do floating point, they've heard of those. They may have heard of MMX. Those are mostly deprecated. Then there's the XMM, but these are growing. And this is straight lifted from the Intel manual, but these have expanded on the most modern architecture to 512 bits wide, so it's quite complex. And then, of course, here's the kind of mechanisms that you have for. Hang on, somebody needs to talk to us. Yeah. So, but these are structures that the processor maintains in the memory. So to get something going, you have to have all this extra mechanism. So you've got to have your interrupt structures in the memory. You've got to have your global descriptor table, local descriptor tables. These go out and point to various pieces of code that you need to be prepared to run on a moment's notice. And then eventually, if you get through all this stuff, then you can come down here to the you've come through the segment management stuff, and eventually you get to the paging. And the paging is a 4-level paging system, so it's quite complex. And then you have this different protection rings, and you have ways, it takes 3 different pieces of protection data to figure out whether or not you've got the privileges to access the data that you seek. And of course, there's all kinds of structures in the memory, and so, and it goes on and on and on. And you have to put all of this in your model if you're going to have a model that's accurate enough to run code. We've been developing this for some time. It contains a state, and this is sort of but the purpose of this slide is to say we have an x86 interpreter, and this is, I would say, defined in the classic sense that we've defined these interpreters for a long time. List-based memory model, very simple, or not very simple, but simpler and easier for us to manage from a verification point of view. Down here, we proved the equivalence of an array-based model that's actually multi-tiered, so we can represent the full 2 to the 52nd byte memory that's defined for Intel at this point. That's the maximum number of bytes that you can address. And so, this happens in constant time. And, it's just another piece of engineering you have to do to be able to run a model at scale, meaning run programs that are gigabytes or maybe even terabytes in size, or in emulation, if you have enough RAM. Okay. How do we know if the model meets the ISA? Well, we do what probably many of you do. We have co-simulation framework that we've set up. We run code on our model. We compare it to what we can observe on the x86. We can do it at various levels of granularity. You can run one instruction. You can look at what the memory and the registers say, and you can compare it to the model memory and registers, or you can run tens or hundreds or so forth. This is a hard problem, and it goes on and on and on. I don't know how to short-circuit it except by taking our model and proving it correct with regard to the design, which is what the Centaur people are trying to do. Our model now supports over 400 instructions, so quite a few. It can execute basically anything that comes out of LLVM GCC as long as it's not generated by some intrinsic where you're trying to capture some latest 512-bit wide special media instruction. We don't have all of those. we've run programs. We have a member in our group that likes to develop SAT solvers, so we take his SAT solver and we compile it into, binary, and we run it, and we can, do various investigations and observe it. And, I'll show you later a supervisor level program that we've actually proven correct. This is 64-bit, and it works for all paging configurations, 4K, 2 megabytes, and 1 gigabyte. Has the segment-based addressing. The model's about 85,000 lines. About half of those are proofs. In other words, proofs about the model showing that some, optimization or improvement or whatever. We're just observing properties of the model, and it's sort of a lot of it's sanity checks in our development of the model. And in some cases, we have to prove that one representation is equal to another, and we do that quite often for efficiency. The simulation speed is about over 3 million instructions a second without using paging. That's before you turn it on, and once you turn it on, you lose an order of magnitude. But that's, it's because of all the extra work you have to do. So the next thing we did once, as we've been developing this model is develop a code framework so we can, a verification framework so we can actually take binary codes and then prove them correct or show that they're incorrect or fail, whichever it is, but hopefully succeed. So what do? We built up a database of facts that allow us to make this job easier. So for instance, this add EDI EAX, well, what does it do? Well, it reads an instruction from memory. That's before you even know what it is. Then it has to read its operands. You're going to write the sum to EAX. You're going to write new values to the flag, and you're going to update the PC. So we have a lemma, if you will, for every instruction. It matches sort of, if you will, on the early bytecodes. Of course, there's all these prefixes and everything, and I'm oversimplifying how it actually works. But we read an instruction, we're going to dispatch on it, and when we go to the dispatch after you've read as many as 5 prefix bytes, then one of these lemmas hopefully will fire, and then you can say it will tell you what the effect is of the instruction on your evolving computation. Okay? And this is a simpler one, this jump equal, read it, check the flags, and then write the new value to the PC, or RIP as it's called there. Okay. So, but to build lemmas about the paging structures, these are quite complicated. And the correct operation of the system depends on a quite complicated invariance that you have to maintain, that the processor maintains, and that you as a programmer have to maintain, or else you're going to find that you've lost control of the thing. All those pictures I showed earlier of all those scattered diagrams and all that, that's the invariant you have to keep in your head when you start doing operating systems level programming. If you don't, you'll get lost. And so we've proved various lemmas that show that we can isolate page tables or the memory management tables from one process to another and show that they're distinct, and then you can show that you have separation. So this is where you can actually show that the mechanisms that are provided by the processor are correctly used to provide that isolation. It's one thing to say you have it, but it's another thing to make the page table entries incorrect and just map 2 things to the same page, and thus you have information flow leakage potentially. Okay? So how does address translation work? Well, okay. Before you ever get here, over here, I won't go into it, but you've got all kinds of whether or not you even are kind of allowed to start the access, whether you can get the necessary task information and so forth. We didn't even put it on the slide because it's horrible, but you have to have it. Once you finally get an address, then it's actually a kind of address which is, a virtual address, if you will, and then you're going to go in and you're going to do the segment mapping. You may not think that you do that in 64-bit mode, but you would be wrong because it does it for certain segments, and those segments for some reason are generated like GS is generated by the LLVM compiler for some kind of stat canary stuff. So you never get away from this crap. It's there forever. So after you go through the segment descriptor and you do that bit of indirection, if you will, then you've got to go through the page tables. And so you finally get this linear address, which is intermediate before, it's after the virtual address. You get this intermediate address, and eventually you want to get a physical address. And then you have to walk through as many as 4 layers of page table indirection. And these are all tables that are in the memory as well. And so to access one thing in the memory, as I mentioned I guess when I spoke on Monday, you may have to go to the memory and I'm not talking about bytes, but I'm just talking about word accesses that you may have to go on the order of 50 times. That's upper bound kind of getting near it, but 30 to 40, that's pretty easy to get to. And so very, very complicated mechanisms. Of course, does that happen in real life? Actually, no, you don't do that very often because these things get cached in like TLBs and other things. So there are many, many caches in the x86 implementations, but for the specification, you just have to assume that there are no caches, or you don't have to assume, but it makes it sort of easier. Anyway, so that's how you finally get yourself to an address. You take your segment, you find where that is, you take the offset, you go and find a linear address, you produce all this, you do all this mapping, you finally get something over here. So that's what we have to get through. And then you also have to know about all the accessed bits and the dirty bits, and all those have to be kept up to date. So very complex. Yes, Gerwin.
So you were saying caches would be nice to ignore, but of course they have behavior, right? So we're doing the same thing, but that's been a headache for a while. So
yeah.
TLB, for instance, would be inconsistent.
Yeah, the point is that the caches can be out of. So if I come along and write this thing in the memory, which should be updated, that doesn't mean it's going to be reflected in the TLB. Likewise, if the TLB may change because you've accessed somewhere in the memory, it doesn't mean it's going to be reflected back into the memory. So this is something, as a programmer, you have to know what you're doing, and an operating system's program should be able to keep that stuff straight, or you would hope so. But our model has enough fidelity that you could do those proofs if you wish to do them. Okay. No, we could, but we don't. But you can still, if you will, have a virtual TLB if I wanted to carry out that proof. Okay? But the TLBs, the problem with that is they're different on every processor, and the implementation and the size and the associativity and whether they have a backing cache, and they're just really much more complicated than you might imagine. Okay? Their implementation. Let's see. We've got some libraries, okay? So let's look at some programs that we've done. So this was something we did years ago. If you've got a model this complicated, can you just bit blast with it? So can you do symbolic simulation? So I'll say the ACL2 system is sturdy enough to do symbolic simulation of that entire program. That's a pop count thing. It's actually was a couple of C routines, but the C compiler merged them, and you can't even find them. So if you went and proved the correctness of one of the C routines and thought you were going to use it as a lemma for the other one, you'd be mistaken because it was gone. And this is why you have to work at the binary level. It's just been erased, okay? And so there's your, binary. And what you want to know is if it implemented Sean Anderson's bit twiddling for doing pop count, and, we just wrote this simple little program. We're showing them in C. We do this in ACL2, but, you can prove this correct with no, on our model, the symbolic simulation of running this 85,000 line model. You can do that with ACL2 with no user intervention. So that's very helpful for taking snippets of code, 10, 20, 50 instructions and just blowing them away, okay? And you need every bit of automation you can have to carry out these things, because everything is like carrying around. It's like working on an oil platform as opposed to home. Home, you have these little nice hammers and little bitty nails like that. That's fine. On an oil platform, the wrenches are all 3 or 4 feet long. They weigh 20 pounds. It's just everything is heavy. Okay. Word count, another thing. Many of you may have done it. You type in Linux or whatever you use. You type WC and space and a file name, and you want to get some information out. For instance, this is the number of character specification, again written in a C style. We wrote it in ACL2. Again, there's binary, and we can prove this. This is a proof by induction because there's a loop in there. So part of it symbolically executes, and then part of it is a proof by induction that a user sets up and does. Okay? 5 minutes left. Okay. Thank you. Other properties, we can prove things about resource usage, and you need to be able to do that to make sure you don't go out of stack bounds, or that you even, you're doing something reasonable. And, if you want to do that, you could do that as well. Okay. So this is the hardest thing I think that's been done, is a zero copy, because this requires operating systems code. So this isn't our hope to be like systems people, but we're wimps compared to them. They sling this stuff around like it's nothing. This is trivial, whatever. But zero copy, the idea is that you rearrange the page tables because you've discovered that the source item that you want to copy is, let's say, on a 4K aligned page, and the destination's on 4K aligned page. Instead of actually doing the copies, you just rewire the page table So you just, can do the copy with no charge. By just rewiring the page table, well, gosh, it'll just appear somewhere else in your memory. So it's much faster than doing the actual copy because you don't have to do any copying. But you have to be able to do proofs about the supervisor structures and all the page tables and all the crap that goes with it, and it takes more work. But I'm just pointing out that it's possible to prove the correctness of supervisor programs that do work like this, and we're doing it, or Shilpy's doing it. Anyway, this is a copy on write style implementation. You're copying, L0, if you will, this block somewhere. But we've wired the page tables, if you will, so that they point to the same physical memory. So you only have one copy of it. So that's the kind of efficiencies that you want for systems level programming. So this proof has been done, and we paused on the updating and accessing the dirty and access bits, although that proof is going on where we do have them all updating because they happen multiple updates per instruction, and it's immensely complicated. We know what it's supposed to be, but we just wanted to get it all working first before then we did all that. So we have different ways we can turn on our model. We can turn it on to be just 64-bit clean. We can turn it on to be full supervisor user mode, everything possible. And then we have a mode that's a little tamped down from that as we are engineering our proof libraries to deal with it. Future work, well, we'd love to be able to run a kernel, but it's probably too aggressive. We need like a hypervisor or something. I know theirs aren't simple. Forget that. They're as much code as Linux. But maybe an SEL4-like thing or some little executive is the right place to start. We're developing libraries to reason about, not about kernel code per se, but just code where you're working on both sides of the memory management mechanisms, and quite. And we continue, and we're interested in identifying invariants in kernel code that might make a system more secure. And so we've been trying to work with the FreeBSD community. We've been going to some of their developer conferences to try to learn what concerns them, and it's quite complicated. So we find immensely complicated. Well, we're just using theorem-proving and these formal models that we've been talking about to do these kinds of analyses, and judge for yourself whether it's of any use to you. But it's kind of like what Peter was talking about, but more narrow, but kind of more flushed out. You can get these things. You can get the theorem prover from there. You can get this if you go to the ACL2 GitHub thing, you can look in a book and get our x86 models if you want, and they continue to evolve. And so that kind of stuff's available. There's some publications if you want to read about some of our things, and there are extra slides. So. Thank you.
Questions? Good. Well, I have one. Non-determinism. I can see how in ACL2 you can deal with reasoning about the range of possible answers, but you were speaking about building simulators. How does the simulator handle with the non-determinism in the answer?
So we have oracles. So we create an oracle, an extra input, and then you can just populate the oracle with whatever you want, and then it accesses and decides, it's in that the oracle provides for all the coin flips and everything.
Fine.
You didn't mention firmware anywhere in there. Is that something you hope SCL4 supplies for you, or you just use
firmware in the sense of that's just software? You see, we're barer than that. We're not there yet.
Okay.
See, this model's not enough. The part whether or not I don't know that we'll be able to build or not, which is my concern about being able to boot anything, is like the interrupt controller stuff on the outside and these other structures that are considered part of x86, but they're not part of the ISA. So we're going to have to rip up holes in our models to put these, I'll say, less pure objects in them.
I like that description, by the way. So this is very cool. I definitely would like to run Cell4 on that. Let's talk.
Hey, and you said it publicly.
Yep.
Everybody, that was Gerwin Klein, and
Yes.
he just said he wants to use our model.
Yes.
I didn't even pay him yet.
What about things like VTX and VTD?
The virtual extension stuff. So he's talking about the sort of the underlying mechanisms to build the hypervisor stuff. We've been looking at it. Again, we have to go to oracles ourselves, and those oracles are like people at Centaur that understand it. So again, we hope that they will tell us enough so we can build something that's accurate, but we don't have the VTDX and VTD stuff yet. There's one behind you there.
Let's take Peter's.
So,
Peter Sewell,
how do you
professor.
How do you test this page table stuff enough to believe in it?
That's why I so desperately want to boot something. Because it's going to crash and crash and crash until we get it working. But this is the way all the simulators are developed. And the other thing, we may co-simulate against somebody else's simulator. So we've been looking at different simulators that are software-based simulators that we can just try to copy and make sure our stuff works like that. But, you know, and then we just have to appeal to the Intels and the AMDs and Centaurs of the world for, you know, to be told where we're wrong. And every so often they'll spend some time and they'll do that for us.
One more question up there.
Greg, go ahead.
Oh, okay.
Thank you. Hi. One question is thinking about going the other direction and synthesizing, say, an FPGA from the spec so that you could run even more test vectors through. Have you given that thought?
That's what the commercial companies do, if you will. And so the 700,000 line model at Centaur can be refined into an FPGA, which they do, and they run it. And the question is can we do that and partition it and make it? Well, yes, we could. Give me some people and some money. So, anyway.
Final question.
Granularity of time. Do you have to deal with anything below just sort of an instruction as a tick, cycles, those crazy clocks in there?
We don't.
Cool.
Thank you very much.